Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 365, I chat with nanomaterials expert Pete Palomaki about quantum dots and MicroLEDs. So stay tuned.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CacheFly.com.
This is Home Theater Geeks with Scott Wilkinson, recorded August 3rd, 2017. Episode 365, Quantum Dots and MicroLEDs. Hey there, Scott Wilkinson here, the Home Theater Geek and editor of avsforum.com. This week's guest geek is Pete Palomaki, owner of Palomaki Consulting and a PhD in chemistry focusing on nanomaterials. Hey, Pete, welcome to the show.
Hi, Scott. Thanks for having me.
So nice to have you here. Before we get started, let me make sure that everyone who's watching live at live.twit.tv can join the chat room there or at irc.twit.tv. And you can post questions as we go, and I'll pass along as many as I can. Always helps to put my screen name in your message, anywhere in your message. My screen name being Scott Wilkinson, my name, no dots or dashes or spaces. That way it shows up in a different color on my screen and I can see it more easily. So, Pete, let's start with quantum dots, which is really what we're here to talk about mostly today. And give us an overview sort of what they are and why they're important to televisions.
Sure. Yeah. So quantum dots are technically a semiconductor. So think things like silicon in your chips in your phone and in computer. But it's a different type of semiconductor, and they're really, really tiny particles of it, microscopic, nanoscopic, really. And these particles take on different properties when they get to these sorts of length scales. And so they can very efficiently absorb light and emit light of a very particular color. And that can be tuned based on the chemistry of the quantum dot. And so for displays, they're really useful to be able to absorb blue light from an LED and convert it into red and green light to give us the three colors for our televisions.
Mm-hmm. Now, we have a couple of graphics I want to make sure everybody can see. Those of you who are watching video, I hope you are. First of all is the structure of a quantum dot. That is graphic number 1. And this is actually, I think we're looking at a representation of kind of individual atoms, right? Within this,
yeah, that's right.
Within this structure.
Yeah. Each of those little spheres that you see in the picture are depicted as individual atoms, and it's listing a core material and a shell material. And the reason that they exist as a core and a shell is to make them a bit more robust and have the desirable properties, like the very efficient conversion of blue light to other wavelengths of light. As just a core-only material, they're not as efficient and not as robust. But once you coat them with a shell and then those additional ligands that are on there, they become more robust and then available to be used in different polymers and solvents and things like that.
I was wondering why there is a shell, and in some cases, we're going to talk about the shells in a minute here. But many of those materials seem to me to be opaque. And so how does a photon get in? First of all, a blue photon get in, and a green or a red photon get out.
Right. So you have to think of it not as a macroscopic property, because these things are way smaller than even the wavelength of light, right? So a blue photon is 450 nanometers, roughly. These nanoparticles, these quantum dots, are on the order of 10 nanometers. So they're far smaller than even a single wavelength of light. And so the way they interact with light is different than the way you and I see it in the macroscopic world of holding a sheet of paper in front of a light or something like that. So the properties that exist are just different at that sorts of length scales.
Okay, and we really are talking about quantum properties. That is the properties of quantum physics, which is definitely a non-intuitive realm, shall we say, right?
Yeah, that's right. We could we could teach, many semesters worth of lectures on quantum physics and quantum dot chemistry if you really wanted to, but I know that's not what we're here to talk about today.
Well, not to get quite that deep.
But yeah, dealing with the interactions of electrons and positive charges within the core of that quantum dot is really what lays the groundwork for their optical properties. And to understand those interactions is still something that the world is learning today. The academic world and the industrial world is still learning how to control those properties effectively.
Mm-hmm. One way to control them, though, if I'm not mistaken, is by the size of the quantum dot. That is, the smaller ones emit higher wavelengths, and the larger ones emit lower wavelengths. Have I got that right?
Other way around. So the small ones
other way around.
emit lower, shorter wavelengths, but that's higher in energy, so it's confusing. And then the larger ones emit towards the redder end of the spectrum. So green quantum dots are smaller, red quantum dots tend to be larger. But there's a lot more. So yes, you're right. Size is one of the key properties to tune the optical properties of the quantum dot. But in addition to size, there are material changes you can make. So changing the composition of that shell, putting on two shells, for instance, is commonly done nowadays.
And one of the advantages of quantum dots is that the spectrum, or the range of wavelengths that they emit, are pretty narrow. And we have a graphic to show that, number 2, which we can see the basically the spectrum, the emission spectrum of the quantum dots there, red, green, and blue. And overlaid on top of that is sort of a more traditional LED kind of spectrum, right?
Right. So the blue in both cases is coming directly from a blue LED. And in the quantum dot case, the red and green is coming from absorbing that blue photon and converting it into either a red or a green. In the overlay there, what you're looking at is a white LED, which is really a blue LED with a broad phosphor that emits all across the visible. But then with the filters involved as well, which filters out the light and gives you semi-pure greens and reds, but clearly not nearly as good as the quantum dots can do.
Let's make sure everybody understands that this term FWHM, which we see a lot when we're talking about the width of a spectral peak like this. What does that mean?
FWHM is full width at half maximum. So it's the width of that peak at half of the height. And so those two dotted lines are representing halfway up the peak height. How wide is that peak? And it's usually 25 to 30 nanometers for cadmium selenide quantum dots. It can be broader for other types or narrower depending on their exact composition and properties. But that's a pretty typical spectrum for a quantum dot that you would use for a display that would give you then really high color gamut for the final display that the viewer is seeing. Right.
I Am Special in the chat room has asked the question that we're actually talking about now. How do you control the output color? And one way is with the size of it, but another way is with the composition. And I wanted to talk a little bit about that because you can make these quantum dots out of a variety of materials, and there is some important things to think about in that regard, aren't there?
Yeah, of course. And in fact, you can make a quantum dot out of pretty much any semiconductor that exists. Their properties may not be desirable. There are certain materials whose properties are more desirable, and I mentioned cadmium selenide is one of those that gives really good optical properties. And indium phosphide is another one that is more recently had a lot of success that shows similar properties but not quite as good as the cadmium selenide type materials. But really, you could make a quantum dot out of almost any semiconductor. It just may not it may not have the same properties as all of the others.
So really, the emission output of a quantum dot depends on its size and the material that you've used to create it. I guess, and there's different materials in the core and in the shell, and that relationship is probably important as well, right?
Definitely, yeah. So as an example, take silicon, which is by far the most common semiconductor that we know and love. You can make a quantum dot out of silicon, and it turns out it emits in the infrared instead of in the visible. So the band gap, which is defined by the composition of the material, is smaller. So you have a lower energy photon that's emitted, and that ends up being in the infrared, so our eyes can't even see it. So silicon quantum dots, for example, are not good for displays, but they might be good for other applications in the infrared.
Mm-hmm. Now, you mentioned earlier that cadmium selenide, is one of the better solutions for visible light, but it's got a problem.
Right. So yeah, cadmium is known to be a toxic material. Cadmium selenide, there's some discussion about whether that as a compound itself is or is not. But yeah, there is an aversion to cadmium in our society, which is to be expected because it has toxic properties. And so the use of cadmium in these in displays and consumer products is obviously something that people are concerned about. And there are rules and regulations about how much of a certain toxic element, whether it's lead or cadmium or arsenic or something like that, how much of that can be in a consumer product. And so there are limits set on that, which is why people are now looking more towards indium phosphide, which there are no such limits. Or if there are, they're more relaxed because it's known to be a less toxic material.
But it doesn't perform quite as well in the application that we're talking about here, which is consumer TVs or displays in general, right?
Right. So cadmium selenide is, for the most part, was the original material that people started making these types of quantum dots with. It was known to be easier to make and easier to study, and kind of gained momentum early on. This was probably in the early to mid 90s in the academic world. And so once people started studying it, more people jumped on the bandwagon, and it's just seen a lot more progress. And it's a material that's a little bit easier to control than indium phosphide. Indium phosphide has a little bit broader peaks, which obviously leads to a loss in the colors that you can display. In addition, it's not quite as efficient typically than cadmium selenide. People have gotten really, really good at making cadmium selenide quantum dots nearly 100% efficient, certainly 90+%, whereas indium phosphide has taken a while to try to catch up. And in most cases, it's still not quite caught up to cadmium selenide materials in terms of the desirable optical properties.
Well, this was a question I wanted to ask you in terms of efficiency. You said that cadmium selenide is close to 100% efficient. And yet, basically, when I think about what's going on, a blue photon of pretty high, relatively high energy comes in, and a green or a red photon comes out. There's a difference in energy. The green or red are lower energy than the one coming in. So what happens to the difference, shall we say?
Right. That's a great question. So the difference basically gets converted to molecular vibrations, which is then lost as heat. So every little bit of loss of energy results in a tiny bit of heat to the system. And so it's basically just heating up the system slightly. And so if you have a 50% efficient quantum dot and every other photon is being converted and every other photon is just being converted to heat, your system tends to heat up a lot faster. Which is one of the many ways that these materials can degrade is by heating up. But if you have one that's 100% efficient and every blue photon is converted to green or red, then all you have is that small loss of energy, as you mentioned, from the down conversion of a high energy blue photon to a green or red.
Right. Okay, and that difference in energy is pretty small compared to the efficiency quotient of, say, 50%, you'd have a lot more energy being converted to heat in a low efficiency situation than in a high efficiency situation.
Exactly, that's right.
Yeah, okay. I Am Special in the chat room has come up with a follow-up here. The size of the quantum dot and the material it's made out does not explain how you force each preferred color. Well, I think that's probably a little misnomer. You're not forcing a color. You're just building a quantum dot that absorbs blue light and emits a particular color as a result of that, right? I mean, it's not anything you're forcing it to do. It's just you're designing it to do that.
Yeah, designing is, I think, the right term. You're designing or synthesizing or creating them to have the properties you want, and so they're made independently. Maybe that may be where there's some confusion. You make a batch of green ones and a batch of red ones, and when you mix them together and make an optical component out of it, you get both the green and red combined. But yeah, you make them independently, you control them independently. They both have their own unique set of temperatures and conditions under which they're made, and that gives you the really fine control of their optical properties.
Mm-hmm. One last thing about the composition, which I thought was very interesting. Actually, we met at the Samsung QLED HDR10 Summit a few weeks ago, and I was so happy to see your presentation there, where you stuck in one of your PowerPoint slides a little thing about the shell of some quantum dots actually being made out of what could be called sapphire. Now, I'm a mineral collector myself, and so that immediately caught my attention. And we actually have a graphic of that, number 3, to show people of the actual sapphire coating or shell on the quantum dot. If we can see that, there it is. So tell us a little bit about this.
Right. So this is one particular company's kind of method to trying to create a quantum dot that's more robust, that will survive at higher temperatures for longer under higher light flux. And this is a technique that's being approached in different ways from various different companies. But the idea here in general is you take your quantum dot that's a normal core shell quantum dot. So this does not replace the initial shell that we discussed. This is in addition to be clear. So this is already a core shell quantum dot. But it's in addition to that, they're adding here an aluminum oxide, which is also known as sapphire. So sapphire is one way one form of aluminum oxide. So they're adding aluminum oxide to the surface, and the idea there is that aluminum oxide might make this system a little bit more robust by protecting the quantum dot from any oxygen that reaches its surface. One thing we haven't discussed yet is that quantum dots, the reason they've taken a long time to come to fruition is because they're really sensitive to oxygen. And so if you make them and leave them out exposed to air, they will not last, not long enough to be in a consumer display. So they have to be protected in some way, and this is one way that people are looking into trying to protect these quantum dots from oxygen, is putting some sort of metal oxide, aluminum oxide, or glass around the quantum dot in order to protect it from atmosphere.
Right. Samsung made such an announcement at CES last January. They touted that what they called a new metal alloy quantum dot. And we actually I found a picture of that as well, 3A, that shows you that they are looking at multi-shell kind of architecture. And I guess they're using zinc, selenium sulfide in one part of the shell, and just new metallic materials, which again are semiconductors actually, but they have some metallic elements in them. And I just wanted to show people that Samsung was making a big deal of that with their latest QLED TVs at CES and since then. So the next thing I wanted to talk about was how are we going to? Oh, before we get to that, I am special. I'm looking at the chat room here. It said, won't they all fire randomly? And the answer, I think, is, well, they'll fire as soon as they receive a blue photon. And we're not trying to control when they fire, just that they absorb a blue photon and emit a green or a red photon, right? Right. And so there are millions, billions, and billions of these things in any optical component. So random is it's kind of random which ones absorb a photon and then they re-emit. But there are so many of them that it's up to the creator of the component to put the right distribution of red and green in such that you get the desirable colors out. And so I'm struggling to come up with a better word than random, but random is probably pretty close to accurate as to
which quantum dots absorb and which quantum dots the photons pass by.
Right. And a follow-up question here is, so each quantum dot is individually addressable? No. The answer is no, absolutely not.
Yeah,
and in fact, that may be...
system.
Can you imagine a little wire going to each one? Wouldn't that be something? No. In fact, that may become clear as we get to the next step here that I wanted to talk about, which is how are quantum dots actually used in TVs? And there are several different form factors, and we have a graphic of that, number 4. Pete, if you could sort of take us through this graphic and tell us what it is we're looking at and how quantum dots are actually used in TVs now and actually in this graphic a little bit in the future.
Right. Yeah. So the first 2 columns on the left that say film and edge optic, any TV that you've seen on the market that has quantum dots in it falls into one of those categories. And by far the vast majority, and this is the case for, I believe, all of Samsung's TVs, is in the film column there, that first one. So the majority of TVs that contain quantum dots have a film of quantum dots in them. And so behind the screen, you have basically a plastic sheet that's embedded with quantum dots, and a blue LED either on the edge or behind the screen, and those illuminate the quantum dots to give you your 3 colors. And then you have your typical color filter after that to isolate each independent color.
So in other words, blue LEDs emit blue light. They pass through this film that's embedded with quantum dots. The quantum dots absorb some of that blue light, but not all of it. Some of it just passes right through the film. The quantum dots, meanwhile, they absorb some blue light and they emit red and green randomly over the entire surface of the film. And those red and green emissions combine with the blue that doesn't get absorbed by quantum dots. And red, green, and blue, as we know, makes white. And all they're doing is making white light, really.
Yeah, it's another way. Well, it's actually very similar to the way that we typically make white light, which is with a phosphor. And this time the phosphor is a quantum dot. And instead of being a broad emitter that is spread over the entire visible spectrum, it's 2 narrow emitters that together with the blue, you're right, make exactly the same color white. And so they're, for the most part, indistinguishable if you just look at the white color that's coming off. But once you start adding in the filters where you get rid of red and blue and just see green, or get rid of green and blue and just see red, that's when you start to see a big difference for a quantum dot television versus a more traditional type television.
Right, because the emission spectrum of green and red and blue, as we saw earlier, is very narrow. And if you can match the color filters to those colors of red, green, and blue, then you will get more light coming out. You'll block less light, filter less light out. And I think it generally makes for an improvement over the previous technology, right?
Right, and it's not only in color, and color is the thing that I think most people think of when they talk about quantum dot displays is, the color is amazing, but it actually makes the display more efficient too, because you have less wasted photons. In a typical display, you have to filter out a large portion of the photons, and so you lose brightness and you lose efficiency. With quantum dot displays, you use more of the photons, so you can kind of choose. Do you want a brighter display and crank up the power on the LED, and or you may have the same efficiency but a brighter display, or have a better efficiency and maybe an equal display to one without quantum dots. So overall, yeah, it's a better technology because it's brighter / more efficient with a trade-off there, and also better color gamut.
So let's go back to the form factors diagram, graphic number 4, because I wanted to make sure we covered the rest of that. So film is what most people use, what most manufacturers use today. A few use this edge optic, which is basically quantum dots in a little glass tube along the edge, right?
Exactly. So remember when I said quantum dots do not like oxygen? That's why this is designed this way. This is a glass tube that's pretty much impervious to atmosphere, and so the quantum dots in a polymer are protected inside that glass tube, so they last a really long time. And so this edge optic has been implemented in many different displays as well as a successful way to use quantum dots in a display. One thing that's worth mentioning is because of the way you engineer this, it's in a tube and not in a sheet. So this can only be used on TVs that have an edge-lit display and cannot be used on TVs that have a backlit array of LEDs. And then on the... Go ahead.
Go ahead. I was just going to head you to the next one.
Yeah, so the on-chip column there, the third one over, is basically moving these quantum dots instead of away from the LED, putting them directly on top of the LED. And so here you see the blue LED with the quantum dots that are actually in the LED encapsulant, which is typically a silicone type material. It's an optically clear material that is pretty robust to high heat and light flux. And so you have these quantum dots that are inside that silicone directly on top of your LED, and then that gives you your color conversion. The disadvantage here is that you have really high heat and really high light flux, and quantum dots don't like either of those things. In addition, you now have taken away either a protective film layer or the protective glass layer in the case of the tube. And so now these quantum dots are exposed to atmosphere, and they tend not to last very long. So this is not currently implemented in any display technology that I know of, but people are certainly interested in trying to go this route because you can imagine that the cost is a lot lower if you can get rid of the engineering of that edge optic or get rid of that large area film that goes in the TV. You can start to address markets that just use any blue LED with a phosphor. Now you can just slap on quantum dots instead of that phosphor.
Right. Let's talk about that.
Sure.
Unless you had something else you wanted to mention.
I was going to go to the QD color filter, but we can stick with on-chip for a bit if you want.
Let's do that. We'll come back to QD color filters. That's farther in the future. I wanted to give people a sense of how LEDs are currently made, because I only learned this not too long ago, and I found it very interesting. We actually have a graphic here called, it's number 5, LED structure, and you can take us through sort of what this is showing us here.
Yeah, so and this is kind of your classic old school looking LED. That's that right. Dome shape. This does not at all look like the LEDs that are in your TV. I promise.
Right. but the basic concept's the same, right?
Exactly. It's very much the same. Yes. Yeah. So yeah, you have electricity coming in from the bottom here, and then really where the action happens is in that semiconductor die there, and there you're forcing electrons in what are called holes, which is a positive charge. It's the opposite of an electron. You're forcing those to recombine and emit a photon. And depending on what that material, that semiconductor die material is made of, will dictate what wavelength that is. And then you've got these various optical components in there, like a reflective cavity and this epoxy lens that help get that light out of the package so that we can actually make use of it.
Mm-hmm. And then number 6 is called phosphor distribution. And here we're going to take a look into that semiconductor die, which I think is really interesting. So tell us what we're looking at here.
Yeah, so the little blue rectangle that you're seeing here is in the cartoon portion is the semiconductor, and you can see it in the microscope image down below. That's the semiconductor that's actually emitting the blue light right there. And then those little particles that you see on top of them are the phosphor particles. And so this can be a quantum dot, or this can be a different type of phosphor. A common one is called YAG, yttrium aluminum garnet. And so those particles will absorb that blue light that's coming out, part of it anyway, and convert it into whatever wavelength they are designed to convert to. And this is showing kind of 3 different ways you can distribute the phosphor particles within that LED encapsulant. And that encapsulant is there whether or not you have phosphor particles. So if you just want a blue LED and just want a super bright blue light, you would take out those phosphor particles and you would just have an encapsulant in there that's transparent. And you would have an LED that's just pure blue with no white light coming out.
Now, and I think part of what the on-chip idea is that you could simply replace or augment those phosphor particles with quantum dots inside there. Now, in that encapsulant, isn't that kind of like an epoxy, a plastic of some sort, and wouldn't that protect the quantum dots from exposure to oxygen?
A little bit, but not nearly enough is the right answer. So yes, polymers in general allow some amount of oxygen to come through. Right? Think about saran wrap on the food that you put in your fridge. You can have the tightest fitting saran wrap, and at some point oxygen is going to get through. And saran wrap is designed to not let oxygen through. It's made of certain compounds that are designed to prevent oxygen from getting through, but it still eventually gets through. And so we're talking about TVs that need to last years and years. And so polymers are not going to stand up to the years and years of abuse that they would see, most polymers anyway, on an LED dye. Only a couple can survive that, and those are, like you said, epoxies and silicones and things like that. And typically oxygen can penetrate those materials fairly easily.
Okay. All right. A couple more questions in the chat room. Game Singer is asking, so quantum dots will never be used as full array backlighting? No, the answer is absolutely they can be used in full array backlighting as long as you have one of these films, right?
That's right, yeah. So in the film application, you can use full array backlight. In the on-chip application, you can use full array backlight. And in the final one that we haven't talked about yet, which is the color filters, you would also be able to use it for that application. So the only one that is restrictive is the tube one that we talked about.
Right. Muchacho in the chat room is asking, the blue LED source seems to emit parallel to the display panel. And I think the answer to his question is why. And I think you're only talking about edge lighting here.
Right. So that there's various types of ways you can create a display, and one of them is with LEDs at the edge of a TV, and the other way is with LEDs fully around surrounding the back of the TV. And in fact, this TV behind me, you have an edge lit display that shines up from the bottom and down from the top and creates the colors, the white light behind the screen.
Right. And I think part of the answer to his question is, yes, the light is shining from above or below in that case, sometimes from the sides, but there's an element inside the TV structure called the light guide plate that actually bends the light so that it ends up going through the perpendicular to the surface of the screen. So it goes through the LCD panels and everything, and you end up seeing the light. So I think that may be a point of confusion there for him. Okay, Robot is asking, could quantum dots be used with a blue laser source instead of blue LED?
They certainly could, and people are interested in doing that. The issue you run into there is that the higher power that your light source is, so a high-powered LED or a laser, the more damage you're doing to the quantum dot. These basically what's held quantum dots back for a long time is the fact that they don't survive, and they tend to lose efficiency over time. And the harder you drive them with blue light, the quicker they die. So the more intense your light source is, if you go to the extreme of using a high-powered laser, the quantum dots probably aren't going to last that long. And so for some applications, that might be okay. For consumer displays, that's typically unacceptable.
Right, right. I wanted to touch on phosphors, because really what we're talking about here in this on-chip application is replacing or maybe mixing in quantum dots with phosphors within the LED. So, for example, I want to take a look at graphic number, let's see, we've looked at LED structure and phosphor distribution. So graphic number 7 shows the spectrum of a YAG LED. So tell us what we're looking at here.
Yeah, so this is a typical white light LED, which really is a blue LED, which you're seeing that sharp peak at 450 nanometers. And then some of that light is being converted to broad white light, which is anywhere from 500 out to 700 or even beyond where our eye can see. And so that broad peak you see from 500 to 700 is the cerium YAG absorbing that blue photon and converting it to those various wavelengths of light.
Mm-hmm. And some companies have been working on improving phosphors. So GE, for example, has this phosphor that the marketing term is radiant red. And if we take a look at graphic number 8, we can see the spectrum of an LED with radiant red, and that's in white, compared with sort of the more typical YAG phosphor LED, which is in black there.
Right. Yeah. So the radiant red is kind of a funny looking spectrum. It's got, it's almost a trident of peaks here. But they're really, really narrow peaks. And so these are even narrower than quantum dot peaks. They're approaching laser-like lines.
Wow.
And so if you can filter out some of those shoulder peaks, you get a really narrow peak then from that radiant red phosphor. And so this is certainly an up and coming technology that's being implemented right now in displays that shows a lot of promise in terms of high color gamut.
But the problem then the next problem is there such a thing as a narrow band green phosphor?
Not yet.
Not yet.
People are trying really hard, trust me, to do that. That's a major hole right now in the industry. Quantum dot greens can be very narrow. And so right now, quantum dot greens are the only narrow green phosphor that exists. And when I say narrow, let's say sub 50 nanometers or something like that.
For that full width half max number.
Yes. The width of the peak is less than 50 nanometers. So quantum dots can do that. Currently, that's the only technology that's out there that can do that, unless you make a green LED, and that's not likely. So people are working on phosphors, similar to those the radiant red. People would love to see something like that, just shifted more towards the green end of the spectrum. That would be a game changer for the industry for sure.
Now, phosphors, am I correct that phosphors stand up to that high amount of light, high heat, better than quantum dots?
It depends how they're engineered. I think there's a lot of phosphors out there that historically did not, and it took chemists and material scientists working on it for a long time to make them robust enough to survive those conditions. So quantum dots are seeing the same kind of technology path. They start out as a really promising technology and good optical properties, but they don't survive. The same thing happens with phosphors, and some types of phosphors, yes, are inherently more stable. Other types of phosphors need to be protected in some way or engineered such that they survive these types of stressful conditions on an LED. So you're right that many phosphors do survive better than quantum dots in these conditions, but that's not true across the board for phosphors.
Mm-hmm. One of the graphics that you had in your presentation that I thought was pretty interesting was the process by which quantum dots could be included or incorporated into LEDs. And we have a graphic to show that, number 9. And I wonder if you would take us through this. I love the slurry.
Yeah, yes, that's the technical word for it.
Technical term.
So you create a slurry, a mix, if you will, of quantum dots. In this case, it's a quantum dot and a YAG phosphor, because the quantum dots here are only red. This is a slide from a company called Pacific Light Technologies, who works on quantum dots, red quantum dots, and you mix that and it creates this yellow, which will emit white light if you illuminate it with blue. And then the rest of the process is identical to the way you would typically make a deposit of phosphor on top of an LED. So you see in that next picture, it's in the little syringe there, and that's deposited via a robot onto hundreds, thousands of little LEDs. You cure that material. Typically that goes through a measurement and binning process. So every single LED is going to be slightly different in wavelength and optical properties, and so they separate them out by wavelengths typically, and then that's assembled onto whatever optical station that it's going to live on, and that's tested or sent to the customer. Right.
Have you ever seen that in action? Have you seen the slurry, which I guess is kind of gooey?
Yeah, no, I've made some myself.
Oh, okay, all right.
You're right. It's think of it like a goop, colored goop, right? I mean, that's kind of what it is. It's an uncured polymer. So polymers typically, when you want to make an optical component, anyways, out of polymers and work with them, they start as this viscous, molasses or honey type material, and then it's not until you either heat them or initiate some polymerization process, and sometimes that's done via heat, sometimes that's done via UV light curing. But you initiate that polymerization, and then they harden and they become the plastics that you're typically used to holding in your hand. But oftentimes those plastics start as some syrupy type material.
And somebody in the chat room noticed that on the last slide, the last step of that graphic, it's talking about like 50,000 hours of lifetime, of operating lifetime, which is really amazing. Is that typical of quantum dots, of phosphors, or is that like the best you can possibly do?
I wouldn't say it's the best you can do, and it all comes down to how you define it, right? It's known that LEDs degrade over time, and so I think 50,000 hours is a pretty common spec for LED lights, for instance. And they say, these will last 50,000 hours, and really what they mean by that is the LED will maintain at least 80% of its initial properties after 50,000 hours, but from day one, it's slowly degrading. And the same is true with quantum dots typically, is they're slowly degrading. And it depends on the application. I mean, with high heat and high light flux, they might not last 50,000 hours, but in other applications with lower heat and lower light flux, they may go to 100,000 hours. So it's very application dependent, but it's a known thing that any optical component like this slowly degrades over time.
Yeah. I'm thinking about... sorry, go ahead.
It might be worth noting here that Samsung has offered 10-year warranties on their TVs that have quantum dots in them for burn-in. And so at least Samsung feels quite confident that this is not going to be an issue in terms of quantum dot degradation over the long term.
Right. Now, they're not putting quantum dots on chip, as we've been talking about. They're using films, probably, maybe tubes, but those have a lot lower heat, a lot lower light flux, and so the quantum dots are going to last a lot longer.
That's true. Yes.
So we've talked about the advantages of putting quantum dots on a chip. Simplicity, you can just take an LED and put it in where you would put the LED normally, and it works the same, or actually works better, hopefully. Don't have to use as much phosphor material. You don't have to change your manufacturing process. So that seems like a lot of good advantages. Yeah. But then there are the disadvantages, right?
Yeah, the disadvantage is that it's really hard to do. It's a very challenging. I guess there's really no disadvantage if you could do it. It's just the challenge of getting there. Right. So as I mentioned, quantum dots do not like being exposed to oxygen, and in that form factor, you can't wrap the whole thing in glass or put polymer sheets on either side to protect it. It's just kind of out and exposed, and that's the way it's got to be. Which is why people are working on different ways to protect those quantum dots. In addition, the temperatures that, say that sheet might see in a TV might be, 50 or 60 degrees Celsius, whereas on an LED, you're talking upwards of 100 degrees Celsius. It gets really, really hot at the surface of an LED. And then on top of that, you just have much more concentrated light flux. So all those photons are coming into a much smaller area. And so you need to absorb a lot more photons in a lot shorter distance, basically.
So before we move on, I wanted to go to that, just talk a little bit about that last category in the form factor graphic that we showed earlier, which is quantum dot replacement of color filters with quantum dots. They're on the right. So tell us a little bit about that.
Yeah, so people have the idea, and they've demonstrated that it's feasible, at least, although it's not consumer ready, that you can, instead of having a color filter that's absorbs and rejects blue and green and only lets through red, let the quantum dots do that. Put a red quantum dot there instead. Red quantum dots absorb blue light. Red quantum dots absorb green light. and they emit red. And so instead of having a material that just absorbs those photons and loses them, why don't we put quantum dots there instead that can absorb those photons and then re-emit them as a useful, as a useful material. So this is green. Yeah, exactly. Same with the green ones. It turns out green ones do not absorb red light, so the red light will pass by the green ones, but the green ones will absorb the blue light. So this takes kind of some re-engineering, though, of the display to make this happen. There's a few polarizers in your display, and this requires kind of matching those around so that the polarizer goes from out of the cell to inside the cell. And we can talk in more detail if you want about that, but it's not trivial. And this is kind of on the display manufacturer's end to figure out how to do this. But if that can be done, then in principle, quantum dots can be used as the color filter. And this has a lot of advantages. Now it's closer to the front of the screen. You can see improved brightness, potentially even more improved efficiency, better viewing angle, which is important to a lot of people. So there's all kinds of reasons you would want to do this. Once again, the reason it hasn't been done yet is because it's really hard to do, to absorb.
Isn't that always the way of it?
Right. This is technology, right? You don't want any of the light leaking through, for instance. If you want just a red pixel, you can't have even a few percent or 5% of the blue or green leaking through, or that pixel's not going to look red anymore. So you need to be really good, or the materials need to be really good at absorbing near 100% and converting 100% of that light to the desired photon in order to make this sort of application work.
Right. So the quantum dots need to be packed together really tight, unlike in a film where you actually want some of the blue light to get through. In this case, you don't want any of the blue light to get through, so they have to be really packed together tight and absorb, as you say, nearly as much, as close to 100% of that blue light as possible before re-emitting then the red light or the green.
Right. Yeah, that's exactly right. And that comes with its own set of challenges optically. Quantum dots are known to reabsorb photons a little bit, which means even though it is emitting that red photon, it actually absorbs a few more, absorbs that photon again in some situations, a very small percentage of them. But the more and more quantum dots you pack in there, the more likely that is to happen, and that leads to a loss in efficiency.
Oh, okay. So it's kind of a damned if you do, damned if you don't in a way, huh?
Right. But people are trying. I mean, there's a lot of smart people working on problems like this that are trying to re-engineer the optical properties of these quantum dots such that they can work in applications like this.
Mm-hmm. And then for the blue subpixel, if I understand it correctly, you don't have any quantum dots there. It's just basically a clear filter that lets the blue light from the LEDs just pass right through.
Exactly. That's right. In fact, I think in some cases that might be too much, and so you actually might want to put in a neutral density filter to get rid of some of that blue light, because it's blue LED going directly through and none of it getting filtered out. But yeah.
Yeah. So that's an engineering problem.
That's easy to solve.
how to yes, more or less how to balance the amount of red, green, and blue so that you end up getting an accurate full color picture. Let's see. There was a question here. Oh, ePony is asking, so the whole effort is to use blue light as the source, but why can't 3 light sources be used together?
That's a great question.
Red, green, and blue.
Yeah, that's a good question. Very, very observant. It can be done. It has been done, but it's very easy nowadays to make a blue LED. It is not trivial to make a green and a red LED. It can be done, but they're typically lower efficiency. They cost more, and it's not done at high volumes like blue LEDs are today. Blue LEDs are churned out by the millions, and because pretty much every optical component that uses LEDs uses mostly blue LEDs with phosphors on it. So it's far less common to make a green or a red LED, but it can be done, and that is one option to getting a similar type color gamut.
I've actually seen a few TVs anyway. Sony used to make one, or Samsung did in its very early days, of full array backlit with local dimming with a red, a green, and a blue LED forming the full color pixel. But you don't see those very much. They came out a little bit a few years ago You don't see them very much anymore, probably because of the expense and the difficulty in making those red and green LEDs.
Yeah, I was going to ask you, do you know how much that cost?
They were expensive.
Probably not cheap.
Yeah, no, they were expensive. They were at the top of the line for sure.
It's a lot cheaper to make a film of quantum dots than it is to have triple the number of LEDs in your screen.
There you go. There you go. Well, yes, and it's still very expensive, but it leads us directly to the next topic of discussion, which you also touched upon in your presentation at the Samsung QLED event, which is micro LEDs. We've talked about that on this show a number of times. So tell us basically what we're talking about when we're talking about micro LEDs.
So it's just what the word implies. It's really, really tiny LEDs. So if you thought the size of the LEDs, in those microscope images looked tiny, those are massive compared to the size of micro LEDs. So we're talking about, 5 microns or something like that.
Right. We actually have a graphic number 10, which shows some micro LEDs.
Yeah, there you go. Yeah. So this is an electron microscope image of an array of various micro LEDs. And you can see that the 10 micron scale bar length there. So these are far less than 10 microns across. They're really, really tiny. And when you get to these sorts of length scales, you can start to think about using each LED as an individual pixel. And so now
a subpixel.
Subpixel. Yes, you're right. Yeah. So each pixel would have 3 of them.
Right.
So if you created an array like this that were all blue micro LEDs, you would have to somehow convert the 2 pixels that are not your blue ones to red or green in order to do that. And that's where kind of quantum dots and micro LEDs are a pretty good match, because quantum dots can do that on these sorts of length scales because quantum dots are so tiny. So quantum dots on that microscope image that you saw there, you wouldn't be able to see a quantum dot. It's so small. It wouldn't even look like a dot on that picture. They're so small.
Except that you said that those are microns we're talking about, micrometers, and quantum dots are in the nanometer range.
Right. So a
1,000 times smaller.
Exactly. Yeah. So they're 1,000 times smaller than those individual LEDs right there that you saw.
Mm-hmm. We have a picture also of a micro LED RGB array, number 11, which I think you had in your presentation as well. And this is what you're talking about, combining red, green, and blue micro LEDs into a full color array.
Right. And so there's people working on this from various angles. So one of the people in the chat room mentioned, can you make green and red LEDs? Well, people are working on making green and red micro LEDs for display applications just like this. In that case, you wouldn't need to put quantum dots on them because they would be generating exactly the wavelength of light that you want. But as we discussed, that's not trivial. There could be a lot of value in just making one single type of LED and putting quantum dots on 2/3 of it to give you your full color.
Mm-hmm. And at one point you made that I definitely wrote down in my notes was that you couldn't even use phosphors in this case because particles of phosphor are larger than those micro LEDs.
Exactly. Yeah. Phosphor particles are often tens or even hundreds of microns across in diameter. So it would look like a boulder in that field of micro LEDs. It would ruin the properties of the display. It's not possible. So yeah, you'd have to either use really tiny phosphors, one category of which is quantum dots.
Right. Well, what happens we've seen a few micro LED displays. The Sony Cletus is one example. The Samsung Cinema Screen is another. I don't know if you've seen anything about those. Cletus we saw at CES. The Sony Cinema Screen I have not yet seen in person. It was shown at CinemaCon a couple months ago, and they've now installed one in a commercial cinema in Korea, in Seoul, South Korea. And they are apparently micro LED displays, which basically are direct emitting. You have a tiny little red, green, and blue for each pixel, and they're sitting in a black well, if you will. And so when they turn off, it looks black, but when they turn on, it's very bright. much brighter than a projected image, and you can tile them up to make any size you want. Have you looked at these at all? Have you seen them?
I haven't seen the actual screen itself. I learned about it at that Samsung event a few weeks ago, and yeah, I'm eager to actually see a display because I hear they look amazing.
They do look amazing.
Yeah. So I'm intrigued to learn more. Although when I asked some pretty pointed questions about what they were doing with the LEDs, they were pretty tight-lipped about it. So unfortunately, I don't know a whole lot about the exact technology. I think because they don't want people to know.
Yeah. It makes sense to me that they would be using quantum dots, but again, we get back to the issue of heat and a lot of light, and these things put out a lot of light. The Cletus, I think the Sony Cinema screen is spec'd at 500 nits peak white, which is roughly OLED territory, but a screen that's 30 feet wide.
Yeah, it's huge.
Yeah, it's amazing. Another question from the chat room here, THX1138 is asking, as quantum dot technology improves, will the benefits of OLED diminish?
It certainly is a competing technology right now, but there are also people that are implementing them together as a technology. So you can imagine a blue OLED material and then put quantum dots on top of that blue OLED material. But right now they're kind of seen as competitors. And if you look at the trends and what people are predicting, there's going to be a lot more quantum dot TVs sold than OLED TVs, and that's mainly because of the cost. OLED is still pretty expensive to make, whereas quantum dots are fairly inexpensive to implement in a TV. So it's unlikely that it will completely squash the OLED market. There are still lots of markets where OLED can do things that quantum dots can't, like your phones, for instance. That's a pretty big area for OLED, but as far as I know, there aren't many quantum dots in phones. But they'll probably both exist for a while. But yeah, they're competing technologies, and quantum dots are probably taking some of the market share from OLED right now.
One thing I can think of that quantum dot has over OLED is, I believe, and correct me if I'm wrong, if you know, that blue OLED material still has a shorter lifespan than red or green OLED material.
That's correct. Yeah, that's what's one of the major things holding OLEDs back is the blue material. And yeah, so quantum dots are better in that regard, that they can last to the required specs for the TV manufacturer for both red and green.
Mm-hmm. Yeah. I wanted to make sure we talked a little bit about the manufacturing techniques of micro LEDs, because you talked about this in your presentation, and I just thought it was very interesting. These two techniques are called pick and place and monolithic. So let's take a look at graphic number 12 and tell us about pick and place.
Yeah, so pick and place, if you remember your childhood game Operation, is very much like a giant game of Operation. Except that instead of picking out pieces out of a body, you're picking out tiny little LEDs and placing them on another on the display backplane, basically in very precise locations. You can imagine if you miss even by a little bit here, you'd see that on the display because the pixel wouldn't be in its place. And so these are made on a using lithography. In both of the techniques you discussed, the LEDs are made using lithography. And then each individual LED is picked off. It's showing here an arm with a 10 or so on it, but you can pick off multiple at a time and transfer them over to then the back plane where you're actually going to mount them for the display. And so that's the pick and place technique.
Okay, before we move on to the next one, you sent me a little YouTube video of pick and place, which I thought was kind of cool. So, Josh, if you can pull that up, it's only about 30 seconds.
Yeah.
Here we go. So that seems pretty easy. Company called Exceliprint. And
it seems easy because it's a cartoon, but it's not easy in real life. Right? And they showed only one transfer of, maybe a couple dozen LEDs, but in reality you have to do that for millions and millions of LEDs, these micro LEDs, to create a display. And so if you're even off one time on that whole display, we would see it on the front of the screen. And that's what makes this so hard, is that you have to be perfect all the time in that transfer from the wafer in which the LEDs were made on to the final display screen. And so doing that over a 65-inch display is not trivial, and it's really hard to do, and it takes a long time, and it's not cost effective at this moment. Yeah,
which I guess is why the Cletus, the Sony micro LED, and the Samsung are both designed around tiling, right? So that they make a bunch of square, roughly, tiles that are embedded with all these micro LEDs, and then you assemble them like Legos to be any size you want. You wouldn't want to do that pick and place thing on a 30-foot wide screen.
Yeah. Right. Yeah. Because one mistake will cost you the whole screen. One mistake on a little box only cost you that little box that you have to throw out. Right. But yeah, you're exactly right. That's one way around it, is to tile them and only make a square at a time. And so your display is created from an array of different tiles.
Right. Right. But then those tiles have to be very uniform, very consistent from one to the next, or you're going to see them.
Yeah, exactly. They've got to fit together really, really well.
Yeah. And exhibit the same color characteristics, so that the color of white of one it must be identical to the color of white of all the rest of them.
That's true. Yeah, we talked about binning LEDs earlier, that LED manufacturers separate them into different wavelengths. Well, that's not try and do that on the for micro LEDs. That doesn't seem realistic to me.
Yeah, yeah. And then just a quick moment on the other technique called monolithic. That's graphic number 13. Let's take a look at that. Yeah. Tell us what we're looking at here.
Right. In the monolithic version, the LEDs, the micro LEDs, remain on the wafer that they were grown or built on. So you don't pick them off and transfer them to another substrate. You leave them directly on the substrate that they were grown on. And so you can now define via lithography, which is well known and well understood now, the spacing of these LEDs and exactly their location. And so this type of technique, you don't have to now transfer them, but you can't do that over a large area. Again, you're either going to have to tile in some way by using multiple of these cut into little squares like they've shown, or this might be more useful for really small displays. Think of VR or heads-up displays or something like that, where the actual screen is a lot smaller. This might be a good solution for those types of displays.
Mm-hmm. One last question. We're almost out of time here. Which is from Mike Heiss, actually, who came back into the chat room. And that is the final use of quantum dots. Let's get back to quantum dots for our last little bit here. And that is as electroluminescent, where the quantum dots are, instead of absorbing blue photons and re-radiating red or green or whatever, they are electrically stimulated to emit the color of light that they emit. That's a little even farther down the road than on-chip quantum dots, right?
Yeah, it's something that people have been working on for decades even. But it's the same story with the blue OLED stuff. It doesn't last long enough. When you build a device like this, the quantum dots don't survive long enough to be useful for a consumer application. But yeah, it's basically, the process is exactly the same as for an LED, but instead of providing that electricity to a macroscopic, say a square centimeter LED, it's now providing that to a film of hundreds or thousands or millions of quantum dots, which are actually providing that light output.
Mm-hmm. Sounds to me like it's much more similar then to OLED, which is another type of material, organic light-emitting diode material, being stimulated by electrical signals and glowing under that stimulation. That's kind of what we're talking about here with quantum dots, but it's farther down the road than on-chip or even than color filter replacement.
It depends on who you ask. People might argue about that. There are certainly people that have made great progress on both fronts, and I think that all three on-chip, color filter, and electroluminescent quantum dots have some major hurdles to overcome. But people said that about quantum dot films, 5 or 10 years ago when they didn't exist, that it was going to be impossible. And look, now it's possible. So
now, yeah, we can buy products that have.
That's right.
Them. Yeah. Wow. Well, it's a bright future, it seems to me, and it's been great talking with you about quantum dots now and in the future, and MicroLEDs. I know you've got a lot of research ahead of you and a lot of work to do, and sure appreciate you taking the time to help us understand all of it.
Absolutely, Scott. It was a lot of fun to geek out with you today.
Very good. Very good. If you want to find out more about what Pete does, you can go to palomakiconsulting.com. That's PALOMAKI consulting.com. You can always find me at avsforum.com. You can email me at scott@twit.tv, and you can follow me on Twitter at avsforum. You can always find previous episodes of Home Theater Geeks right here at twit.tv/HTG and on our YouTube channel, which is youtube.com/twit Home Theater Geeks. Next week, my guest geek is scheduled to be audio legend Bob Carver, who is going to come and talk about his latest tube amps, line array speakers, and certainly plenty of other interesting stuff. The guy's quite a character, and he's been a serious fixture in the audio world for decades. So I'm really happy to have him on the show, and do hope you will join us for that. Until then, geek out.